Hello. So, my name is Chris, and I'm going to deliver a talk on an introduction to distributed databases, the concepts of them, and what they mean to your programs. So, I have a fairly varied background. I've been a musician, and I've lived in various places around the world. I have been a programmer since about 1998, but mainly in PHP and more traditional setups like MySQL, connecting a PHP framework to MySQL. And for some reason, Crate, the company I work for, and we make a distributed database, liked my personality and employed me to work in developer relations, even though I didn't really know much about distributed databases at the time, and I'm still learning. So I guess this is a talk that I would have liked to have seen 6 months ago when I started, because I didn't really know a lot of what people were talking about to me. So it's a sort of introduction. I don't pretend to be an expert yet, but I want to introduce you to some concepts. So if we're building any sort of application at scale that's processing lots of data, is reading lots of data, then to be blunt, we can no longer just have one instance of a database. This is not a new idea really at all. In fact, now most web and other application stacks are moving towards distributed databases. They're more resilient, more flexible, and more able to work with modern infrastructures. And I'm being careful about not selling buzzwords as a silver bullet after the first talk I saw this morning. Other options are available, and we'll look at good use cases for some of these later. So with a traditional database, let's use MySQL as an example. It's a perfectly good database in lots of instances, but there are certain instances where it starts to get hard to make it work better with large sets of data. So traditionally, let's take the story of a startup, a small startup. They start with MySQL and decide that maybe it's lack of flexibility. They need a document storage as well, something like MongoDB. What this means is this is a breed of NoSQL databases, and what NoSQL and document databases means, instead of everything being stored in tables with rows and columns, we actually have key value pairs, basically like JSON, if you've ever seen JSON, which you probably have, stored in actual files. This is the concept of a document database. And it gives you a way of structuring schema, structuring the type of data as you go. And we'll look at some examples of that shortly. Once you start to have this sort of collection of technologies, we need a way of searching it all. So we add a search mechanism as well. Maybe we want to store binary objects, images, files, and things like that. So we add blob storage. And then we would use various techniques to synchronize and replicate our data. And maybe we use partitioning and sharding to break up our data into more manageable sets. And in this case, we have two types of partitioning. There's horizontal partitioning, which is what I'm referring to here, which is sharding, which we split the different rows into different tables, maybe by zip code, postcode, date, things like that. Or there's also vertical partitioning, where we actually split the columns instead and have to sort of assemble and reassemble the data when we read and write to it. None of this is complicated per se, but it's complex, and it can get harder and harder as a project matures, as an application matures, and we end up spending a lot of time on these sorts of methods instead of a good application. So this is where distributed databases like to try and help, if it suits your use case. Equally, we now have things like containers, microservices. Whether they are applicable to your application or not, they are becoming increasingly popular, and this is where languages or services come and go very quickly in isolated containers or just as services, like Amazon Lambda, for example. And whilst these work very well with certain instances, when it comes to databases and keeping that data persistent, reliable, and available as these services come and go, that's also an extra challenge. Again, not impossible, but an extra challenge. And again, distributed databases try to make this easier as well. So what are some of the concepts of a distributed database? Well, often they're aiming at an increased performance, an increased ability to handle large data. So often a lot of functionality and features that you might be used to in a traditional database, the focus is actually on the application to handle a lot of that instead. And we'll look at some examples of that. So there may be some extra steps you need to take in your application to handle working with these sorts of systems. We also, each option tends to weigh up availability versus consistency. Consistency is how reliable the data is across the instances of the database. Availability is largely speed, performance of reads and writes. So each option will weigh up what they feel is important out of that balance. And again, you choose an option that works for you. So in a traditional setup, looking at sort of the slide we had earlier in a bit more detail, this is how we would scale MySQL, for example. We would have a database master, which we trust, maybe. It's on a server infrastructure that we feel is more reliable, we trust it, it's a faster machine, etc., etc. And then we have slaves, which contain either partitions of that data or maybe complete copies of it, who knows. And then a load balancer handles requests to the applications and divides them accordingly. And if we wanted to increase this one master and 3 slaves, we would add more masters and slaves. Again, not complicated, but complicated enough. And a distributed database uses a concept of horizontal scaling instead, where effectively every instance of the database is kind of the same and can kind of perform the same functions. And in practice, you may differentiate them slightly, but in theory, they could be if you wanted them to be. So if this cluster here needed 4 instances, we would add a 4th, and it would handle it. And I will show you a demo of this to make this clearer. But just before I do that, so in our case, in Crate's case, this is kind of what each instance is able to do. It's able to handle transport between each instance, it's able to parse queries, execute queries, and be able to be interacted with by HTTP as well as several other things. So this might be easier with an example, a simple example. I wonder if I can get that resolution a bit better maybe. Probably not, but we'll see. Oh, that's better, good, okay. So I have a cluster here. I'll double check I'm still connected to the internet that works. No, I'm not, so this may or may not fail. The problem with working with big data is it's very hard to demo it from your laptop because my laptop cannot cope with 150 gigabytes of data. Okay, that's good, right. So this is a demo cluster created that has Github Archive data, and we'll look at that data in a minute. It doesn't really matter too much right now. What's important to note is we have 12 nodes up here. This is our Crate interface, but most other options have some kind of interface like this that we can just get an idea of overall cluster status. It's running on AWS over here. And they're all reasonably high-spec machines. we can see each instance in the cluster here and get some overall information about it. And we can see the schema here and those partitions we mentioned. So we've partitioned here by date. So at the moment, you can see that we have 100, I think the text is a little, I think just about readable, about 150 million records, and we have 100% replicated data and available data, and we have this nice green health indicator of good. So what I'm going to do is I'm going to go into the AWS console and just reboot one of them. So remove it temporarily from the cluster. And we should see quite quickly, bearing in mind internet connections, which you can always blame in live demos. Yep, there we go. It jumped to yellow, and we now have 24 million, it just changed to 21 million records under-replicated and only about 85% consistency at the moment. If we jumped into the table, we can even see the partitions that are most lacking in consistency right now. If we left that 12th instance unavailable, the cluster would resynchronize eventually, quite quickly, but maybe in a few minutes. But as the 12th one will rejoin it pretty soon, it will become consistent a lot quicker. We can even see that some of those that were yellow have become good again. So this is kind of the principle that theoretically we can let this sort of auto-magical, I hate to use that word, but for the sake of this demo, let's call it that, synchronization to rehandle changes in scale. If we added more or took more away, the same sorts of things would happen. And this is working quite nicely. It's rebalancing quite well there. I would guess the 12th one is probably, no, it's not. It's still not available, but it's jumped up to 97% now, quite rapidly. So that's kind of an illustration of what happens in a horizontally scaled distributed database. Just very briefly, because people like to know this, and I won't go into too much detail, but this is sort of what Crate is using for lots of its technologies. We are using lots of open source components, a lot of Elasticsearch, but a lot of other technologies, and then the blue are our own contributions, but the whole is also fully open sourced as well. I've always worked in open source, and I would never work for a company that did anything else. So that's some ideas of what's going on there, and if anyone wants to know any more about that, you can talk to me afterwards. So bearing in mind what we saw, that especially in an eventually consistent system, where data becomes available eventually, and eventually is a rather general term, what that means depends on many, many things. How do we cope with that? There's a couple of different sort of new things we need to think about in our application logic when we are handling this sort of system. One is, of course, we check, has the data been updated? And this is what I was alluding to, you have to rethink your application a lot of the time. The focus is put on the application. So if it's important to your application's logic that the data needs to be 100% consistent across the entire cluster, then you may have to pause processing temporarily until it is again. Or you can check specifically where data is consistent. So if you needed the partition of 5th of March to be 100% consistent, and that is, then you can carry on. But maybe if April isn't, then you don't, et cetera, et cetera. So, and there's lots of checks to handle this. Usually there's metadata in the tables, in inverted commas, because they're not really tables, but we'll call them that for now, to check, has it been updated? What's the latest version? How consistent is it? And proceed or not accordingly. And equally, a lot of this tends to happen automatically, but if you want to explicitly refresh your tables instead, you can. And generally you would find a setting, disable it, and you can handle the sort of automatic refreshing of data yourself in an application. So these are some of the very basic principles. So whilst like when I showed there, it's very simple to let the cluster manage itself, your code does have to react accordingly. Not to say that it's that complicated really, but it's an extra thing to think about maybe. So because of this, because there's some new concepts to learn, a lot of these databases will offer very easy ways to get started with a variety of language clients available to sort of plug into your application to get going. And some of them, where relevant, things like Ruby and some PHP frameworks will even offer things like object relational mapping and let you map model objects in your framework directly to schema and handle that a lot simpler. Equally, a lot of these are designed to run maybe millions of rows of data upwards, processing gigabytes of data. If you're not looking at that kind of scale, and there's probably an overhead that isn't worth it, but if you are, then the infrastructure needed to support that is obviously also going to be a little more complex. So many will offer ways of easily getting started, things like Docker images, things like going hand in hand with that, container orchestration like Mesos, and there's a Mesos talker straight after me after lunch, which is really good because it'll follow up nicely. Things like AWS images to get you started very quickly, things like Google one-click installations and Azure images and software and et cetera, et cetera. So let's look at some options, some choices, some examples in this world. It's a very busy space. It's probably almost as busy as JavaScript frameworks. I would say JavaScript frameworks, one every week. Distributed databases, maybe one a month. I don't know. It's quite a busy space, but a bit more complex. So there's lots of options. And I have always people say, what about X? What about Y? Well, I can't mention everything. I have generally gone, firstly, for ones that are not software as a service. They're all open source, install yourself if you want. They usually have SaaS options as well, but that's so they can make some income. All of them claim scalability, of course. There'd be no point if they didn't. All claim things like data center replication. Again, at this sort of scale, you'll probably have your data and machines handling the data spread across many data centers around the world, so they need to be able to handle that. All are NoSQL based, that document storage that we looked at earlier. All of them use that concept, even if it's hidden from you. And so I've picked a couple of the sort of main names and maybe a few outliers as well. So to make some comparisons, I mentioned the GitHub Archive data. We're using that data. Why? It's a very good data set to work with to show the sort of features and commonalities amongst these systems. Firstly, it's fairly large. Every activity of every hour of every day since 2012, every public activity, I should say, for any of you who run private repos on GitHub and are worried. It's not a massive data set, but it's pretty big. It's about 200 gig, which actually for 5 or 6 years data is not a massive amount. GitHub is popular, but it's not Facebook, but it's a lot of data. It has lots of nested objects. Repositories have people who acted upon them. People who acted upon them are part of teams with other people who act upon other repositories, and et cetera, et cetera. Different activities, so create events, push events, give different row contents. So data changes. Data changes each year as well. The data in 2012 is not the same as the data in 2015. And one of the great features of NoSQL style databases is that schema can change over time, and the database doesn't really care too much. Your application, if it's running queries, of course, may need to change, but the database will just keep storing it anyway. So it's a very good example to use. And of course, developer conferences, so what better to use? Here's an example, a very simple example of when you pull the data down from the GitHub Archive, you get tarball JSON files, basically. Here's an example of a create event, the person who acted upon it, the repository, and some metadata about what it was, basically. It's a very simple example, but it's an idea. So to sort of compare and contrast, I made a very basic query, which was select the user with the most amount of activity on their repos. So let's say the most popular user of GitHub, basically. A Doing this in standard SQL would look something like this. Select the login name of the person, give it an alias, count, give it an alias from the table, group by the name, and then order by the amount of logins and top 10. Now, I'm going to tempt fate again. Let's actually run this. I know the results, unfortunately. I've done this talk before, but you haven't. So let's see. Oh, actually, I did meet someone who saw me do this talk in Belgrade, so maybe you have. We'll see. Let's get that resolution back again. So we're processing about 150 gig of data right now and performing some functions on it. So it takes a little bit of time, and it's just a demo cluster, so not the best optimized. And I blame the Wi-Fi, of course. So let's see. Hopefully, there we go. Okay. It hasn't really changed since the last time I looked at it, but I don't think you could even read it, which is, it looks like Klingon or something, doesn't it, at the moment? So I'll have to read it to you. The most active user of GitHub is the Google Code Exporter, which is a bit disappointing. And then second to that is Direwolf, who I'm not entirely sure who that is. But we're looking at hundreds of thousands of logins. So I guess they must be automated systems or someone who really loves GitHub. Yeah, looking at them, I think a lot of them are automated systems. But there we go. Anyway, we get an idea of what the query returns. So, our first player, MongoDB. This is possibly one of the older ones in the field. You've likely heard it, maybe even used it. Its consistency model is a lot like many of the others. It strives for consistent data on the prime, the sort of master in the cluster, and then eventually consistent across the rest of the cluster. It uses its own way of querying. It doesn't use SQL. Many of these don't. Open source plus support, big name. They all claim big name clients, of course. And to get things like binary storage and full text search, we have to add some other options, but we may not need those anyway. So recreating this query, it's a little unfair because I kind of am trying to convert SQL to databases that aren't SQL databases. So you can't always do similar things. That's sort of the point. A lot of these are not fully relational systems. So often you don't have concepts like group by. You don't have concepts like joins, joining related sets of data from different places together. And that is what gives a lot of them the speed benefits in the first place. And we'll look at later, if you need those kind of features, this may not be the best options for you, but we'll look at some use cases later. So it uses this sort of, again, like JavaScript, JSON-esque syntax. Once you sort of break it down, it's not that complicated. It's not a very complex query, but it's not that complicated. We pick the field we want. We group it by a unique key, which is the username, and we say we want to sum each one of those. We sort descending and limit by 10. It's actually, once you look at it, not particularly complex, but a little different. Next one is Cassandra. This is an Apache project, I think originally built by Facebook, but it's an Apache project now, so fully open source, has a pretty stable long life ahead of it. Its consistency model I put a question mark next to because I couldn't get a complete answer, which probably means it's up to you. You can decide. A lot of the other commonalities, open source, commercial support, third-party SaaS providers, etc., etc. It's quite popular. It also uses its own custom query language, but it's very similar to standard SQL. So here there's a couple of very slight differences. One of the smaller ones is it has this concept of key space names instead of databases. That's not that complicated. The other one is the absence of a group by. There is no group by. That's not unexpected. So you'd have to do something else to handle that. React is one of the more possibly harder options to get going with. It has a tremendous amount of configuration options and things you can decide on. But if you don't really know how to start, then that's hard because you don't know where to start. So what do you configure? So yes, I found their documentation quite hard to follow as well. It uses, well, it has various concepts around queries, and I'm going to come to that shortly. But again, the consistency model is up to you. So let's have a look at the query, and we're going to take a little bit of a detour around some concepts. So it does, it gives you lots of options, but one of the options I've highlighted to make it more interesting is for its sort of schema, creating queries. You can do the object relational mapping. So you can actually just use one of its language plugins to map your models in your application to the database directly. And it kind of encourages that. And actually, if you think about it, that's a nice, tidy way of doing things, really. And you're likely to have that kind of framework if you're at this sort of size anyway, I guess. The query uses a concept called MapReduce. And I'm going to take a little detour into what that means. This was pretty much the best picture I could think of. This is we have an office down in Berlin, just about here somewhere, I think. It's an area very popular with protests. And I think there might be one happening here at the time of this screenshot, actually. I'm not sure. So MapReduce is a programming model generally used a lot with generating and processing large data sets, especially in fact, pretty much only in distributed parallel systems. It's two sets of functions, and the way the language they're written depends. But the concepts are that the map function filters and sorts the data. It takes these sets of key value pairs, processes each of them as you decide, and generates 0 or more outputs of the key value pairs, generally different. In our example, it isn't different because we're basically just taking every user, we're sorting them, but we're not filtering them in any way. So it doesn't change that much. Then next, it will call the reduce function, which performs other operations on each unique key. So in our case, it takes all the input values and sums each unique value, giving us the final sums. So that's kind of the concepts. It's a fairly big topic, but as soon as you enter this world, you'll see it mentioned all the time. So it's something worth trying to understand. And I'm still understanding it myself, but this is kind of the overarching principles. Which leads us to another that uses this kind of concept. Couchbase has done quite well, I think, for themselves in terms of offering open source versus commercial options. Pretty similar ideas for consistency and all the other options. And it uses its own custom query language, again, which is on these similar concepts. They have quite a nice admin interface that when you install is made available to you, where you can play around with your data in these little MapReduce boxes, and it'll give you a link at the bottom that you can click on and then see the results. So it's a good one for experimenting with. And here you can see I've sort of recreated that query. And it's the best way of sort of illustrating how it might work. An outsider or an outlier in this is Cockroach DB. This is being worked on by lots of ex-Google staff, which always generates lots of interest, especially in America. It seems to be promising just about everything that you might want. It also promises something called transactions, which is not that common in distributed databases, which will ensure that data is processed in a particular way, in a particular order, and you can rely on that. And strong consistency everywhere. It's very early days. They're just starting to hire lots of developers and other staff members, so it'll probably start progressing quite quickly. But its documentation is a little light on details at the moment. So in terms of representing a query, they claim they're going to support full SQL, but I don't know. So that's kind of my summary right now. But it's an interesting one to watch. If they do deliver all they promise, it could be an interesting one to watch. And finally, here's us. we kind of we're just a small startup, so we're aiming pretty much primarily on performance. So it's eventually consistent, as we saw in the demo. We don't support transactions, but offer lots of other functionality. So kind of about ease and speed, basically. We do use SQL, or at least a subset of SQL, and I cheated because that query I showed earlier is basically, as we saw, kind of the one that we started with. So that's us. So earlier I mentioned about containers, and this is something that is an extra issue because as containers come and go, how do we keep that data available? So I'm going to do one very quick demo and then sort of expand upon it and then wrap up. So I'm going to I have Kitematic here, which is sort of Docker's little visual installer for Mac, which is quite useful. And very nicely of the Docker team, we've ended up on their initial, right at the bottom, but still. And this has actually given us a lot of installs, which is very nice of them. But I'm going to jump to the command line. So if anyone has or hasn't used Docker before, other containers are available, but it's very good for demos. I'm going to create 3 instances. There's not a lot of point having a distributed database with only 1 instance. I create 2 here that we just run in the background and let Docker allocate the ports needed between the host system and the containers. And you can see we have 2 instances there with the nice log files opened up already. And we'll create 1 more that manually sets the ports that we like to use. Okay, and that'll be the one that we sort of interact with. So I'm just going to import some tweets to get some data. Oh, there we go. So when all the containers are on the same system, they can communicate with each other through a concept known as service discovery. And there's different ways to accomplish this. And when it's on the same system, it's something called multicast. It's very easy. We can almost just turn everything on and let everything run. And I'll stop the import. And without any effort on our part, those 3 nodes have discovered each other and are running completely fine. And if we added a few more, add a lot in succession to make something change, we would see that this, like we saw earlier, would temporarily rebalance. That's still picking it up any minute now. And again, as they're on the same system, we don't really have to worry too much. They find each other, and as containers come and go, the data is balanced. There we go. That's it. Now it's starting to change. That's it. They're going up now. This is great, but this is not very real world. Most of the time, unless we're just doing a local demo, containers are not all on the same system. It kind of goes against the point, really. And we have to do a couple of extra steps. And this is just doing its thing, so I'll jump back into and show you. That's the basic one I just ran. So in this case, we do a couple of extra things. We make use of the way that Docker in particular lets us map a local volume to a volume in the container. And we, in the crate configuration, we say that this is where data can be found. This is one way of saying that if we have, say, 5 virtual machines, each with a container each, and on one of them a container goes, if one comes back again, it can pick up the local data store that was already there, and whilst it could use the discovery amongst the cluster to find the data it needed, it's far quicker to pick up a local copy and just resynchronize what's missing. So this is one way of keeping things persistent. So through the combination of those two options, it's a lot easier to keep container type infrastructure persistent. And I said that lots of these options will use multicast by default, but that doesn't work across multiple machines. So in this case, we're using unicast to just manually set the hosts that are in the cluster. And that works, it's pretty simple and works well, but it's not very dynamic. Containers are naturally a dynamic system. Manually setting a list of IP addresses is not very dynamic. And there's many quite good solutions to fix this now. There's something like Weave, which is particular to Docker, that lets you create kind of a virtual soft network across your network, and then they will find each other through that. If you use AWS, they have their own DNS discovery service, so you can set a DNS query and they'll discover the members that match that. We now also have that same DNS discovery built in just to Crate as well. You also have things like Kubernetes and Mesos for container orchestration. And Mesos, for example, can handle non-containers as well, which also have their own DNS type way of discovering each other. So it's a common way of doing it. And as I say, there's a Mesos talk after lunch, and hopefully that will cover some of that. So whilst initially it may seem a little bit more complicated, it's actually very easy to get that working now across data centers, across machines, even mixed infrastructure. So that's kind of a wrap-up of everything, but where a distributed system is useful, they're not useful for everything. If you do need transactions and aren't waiting for Cockroach, then if you need transactions, this is fairly important in financial records, for example, then it may not be the best system for you. If you want strong relational data, things like those group bys and joins, again, may not be possible. Often it can be replicated in your application, but not always, and it can be a lot of work. We personally are working on joins in Crate, and it works, but it brings the performance right down. So it's a complex problem to solve. We're trying, but it is hard work. So that's sort of the use cases where it may not work. But where are these great and where are they often used are things like sensor data. Data that is rapidly processing, changing all the time, and isn't like mission critical. If it all gets recorded in an exact order, it can be sorted out later. So business intelligence, marketing intelligence, network security logging, device logging, things like that are all perfect use cases. So, I've got us on time for lunch. Well, you were running late, so I've helped get things back on time. So, and that's our details. We're a startup, so of course we have merchandise. There's some great t-shirts and stickers here of varying sizes and genders, so please take some. And if you have any questions, ask now or come and have a chat to me afterwards. But thanks very much.